Ladies and gentlemen, today we are going to tackle one of the most advanced technical problems in healthcare. Please welcome bone doctor. The context is that when you come to hospital, an X-ray is taken, then our program does something and an assistant looks at it. So we try to provide some guidance and help them make better decisions and faster. So one of the things, we decided to do 3 projects instead of just 1. And the first one is refining the X-ray to make it more visible. So if you look at the input image, you can clearly see that the outputs are much more visible and helpful for the radiologist who looks at the X-rays. The data set that we had has huge diversity. It contains 40,000 images, 14,000 studies, and we try to normalize all of the images into a unified format for the radiologist. So no matter in what format we get the data, we always get something that is clearly visible at the end. For example, these are some examples. In the second picture, we detected that we have to invert the inner part of the circle. In the first example, we managed to turn a black image into a bone. Then the second feature, the second part of the project, is actually finding whether it has a fracture and maybe locating where the fracture is or any abnormality. So for that, we use machine learning that classifies whether a bone is broken or not. This example has maybe a slightly visible fracture where the bone is broken. We also classify other cases that are abnormal, not necessarily containing a fracture. Then we use special hashing of pixels and their neighborhoods to find something that may be the abnormality, which we then try to highlight and locate. And the first, maybe most advanced part is to find similar cases. So basically pictures that are of X-rays that are healthy of other patients so that we can compare the input image with.
Yeah, so the way we do this is via the clustering of images. So each image, we have multiple views of multiple body parts. And then what we want to do is to do a cluster of images so that we can group similar images into the same cluster. But by clustering just raw pixels themselves, they don't really tell us a lot about the images. So what we do is we take an image and the image encoder, Inception V3 network, and get an intermediate output layer of the network to represent the image into a feature vector. And then we cluster the feature vectors. So if you can see on the screen, we have like all the images of the similar view of this certain body part, the hand, into one cluster, and the next one looks distinctly different, but they're all of a similar view within the same cluster. So one way we want to do to get the similar visual images given an input image is to compare the cosine similarity of the feature vectors between the images themselves. So given an input image, a high score image will look quite similar to the input image, and a low score image will look very different from the input image, even though they are from the same cluster. But the problem with this approach is it's kind of slow. So in order to speed up the process of comparing the number of feature vectors and computing the cosine similarity within the feature vectors, we have to do image hashing to reduce the number of images that we search from a few thousand to maybe around 20 to 30 images. And this will be done by the image hashing. And yep, our similar images will look something like this. So if you have an input image, you will give us very similar image of like a flat head. So yep.
So what would be even better if we could somehow find a mapping from the pixels of the input image to pixels in the matches that we found. So how do we do the mapping? Well, we define a set of transformations that we can do. We throw a lot of arguments on it. We then evaluate how good the match is between two images, and then we do that over and over and optimize. And with that, we can come up with basically an overlay. This is like a function that maps the pictures in the input image in the pictures in the output image, like the match that we found. And this allows us, or allows the radiologist, to look at one part of a bone and actually have it compared to the same part of the same bone with other patients who had the bone healthy. So this is something that we consider to be most helpful. This is the pipeline, basically a simplified version of how the components are put together. It's not really that important, but basically it's a computational graph that recomputes whatever is needed whenever any of the user input changes, including like the algorithms that the user can choose. Although we do not do user interfaces, we do science, yet we have created a user interface for the clinician to preview the results. That's it, thank you.